Okay. First thing I want to clarify about the formulas that will be provided in midterm. So in the previous document, I think I told you that I'll provide the coordinate transformation formula between different coordinate systems, and then I told you that I'll provide the gradient, the curl, and the divergence for the cylindrical and circle coordinates. Okay, but still, okay. Some of you ask me more want to know exactly which formula will be provided. So here I just decided to just show you okay what exactly okay will be provided in the midterm test. Okay, the formulas. Okay, so I show all the formulas here. That does not necessarily mean that you need all of them. Okay, first of all. Okay, so my original plan was to actually just only give you the one that you need. Okay, in the problems. Okay, but since some of you asked me questions about the formula, so I decided to just put all these formulas. So anyway, whether the question will be about these or not, okay, I put all the formulas, okay, in your midterm question paper. Okay, so I will upload this document to Blackboard, okay, after the class. Okay, so you can see what you got here, right? So for cylindrical coordinate system, so you know how to transform the XYZ point to the rho phi z, right? So and then I give you the unit vectors, okay, the differential area elements, the differential volume elements, and then the infinitesimal displacement, okay, gradient, divergence, and curl. Okay. So same thing for the spherical coordinate systems. Okay, coordinate transformations, unit vector, differential area elements, and differential volume elements, infinitesimal displacement, and then the gradient, divergence, and curl. Okay. So these are the formulas that you will have anyway. So, but again, I have to say that it does not mean that you need all of them. Okay, so that's the key. Okay, but just to make things clear, okay, so don't need to worry about which one you need to memorize and which not. So refer to this. Okay. Okay, any questions about the formulas will be provided in midterm. Okay, if not, okay, we'll continue on the chapter of ODE. Okay, hopefully we'll finish this chapter or almost finish this chapter today. And then after the midterm, we can open a new chapter. Okay. Test. Okay. Okay, so last time we have done some problems on this second order non-homogeneous linear ODE, right? So the key is that when you see the second order ODE where you have the right hand side, right? The right hand side to be non-zero, right? So then all you need to do is to find two parts of the solutions and then sum them up, right? So the first part is called the complementary solution, which can be obtained by just setting the right hand side to 0, right? So that becomes a homogeneous ODE, right? So then you get the so-called complementary solution, and then also you find a particular solution, okay, which is the solution of this whole equation here. And then the general solution, right? The general solution of this non-homogeneous ODE will be a sum of the two, right? So and we did some practice problem, right? So and the way that we found the particular solution is that we try some form of the solution, right? So given by considering what kind of form that you have for the g of x. Okay. So before we move on to the next method, okay, so let me make one remark here. Okay, one remark here is that so we have been using this concept of this non-homogeneous and homogeneous differential equation for second order ODE, right? However, if we just take one step backward, okay, actually this concept also applies to the first order ODE. Okay. So for first order ODE, okay, for first order linear ODE, right? So you probably still remember this form, right? So in general, a first order linear ODE looks like this, right? And now we can also say that this is a non-homogeneous ODE because of the fact that the right-hand side is not zero, so the function here, right? So if I have a homogeneous ODE, right? So then it will just be this one. Okay, so then this is just homogeneous, non-homogeneous. However, okay, so remember how did we solve this problem for first order ODE, right? So we use the general method, so-called the integrating factor, right? So integrating factor, then just once and for all, we solve the full solution for this equation. We didn't really say that, okay, it is composed of two parts, right? The complementary solution and the particular solution, right? However, we actually could see it that way, right? So let me give you one example that you have probably seen, right? So if you want to solve this, okay. So this is a non-homogeneous linear first order ODE. And if you still remember the method of integrating factor, right? So you immediately find that the solution is, the general solution is this. So using integrating factor, that's it. So however, right? So if we just use the concept that we learned last time, that the general solution of this equation can be treated as a sum of the complementary solution and the particular solution. Okay, what you would do is the following, right? What you would do is that okay, so you look for complementary solution. Okay, so to do that, you set the right-hand side to be zero. So then you will have this, right? And of course, this is just a very easy. This is just a separation of variables, right? So you find that the complementary solution is actually this one. Okay, so when I'm doing this, okay, just pretend that you don't know the final answer. Okay, so now the particular solution, right? So then we look for particular solution. So what do we need to do? So we look at what it looks like on the right-hand side, right? So it's 6. So then we know that the trial solution that we are going to try is that we just try yp equals to some constant a, right? Because this one is the constant function. The g of x is a constant function, so the trial solution will also be a constant, right? So then if you do that, right? So then you will have this dy p dx minus 3yp would be equals to just minus 3a, right? And that has to be equals to 6. And that means a is minus 2. So that means your particular solution is minus 2, right? So then your general solution, right? So it's the sum of this yc and yp, which is ce to the 3x minus 2. So exactly what you got here. Okay. Of course, it has to be the same, but just to remind you that this is a different way of seeing the problem, right? So we have been talking about this homogeneous and non-homogeneous, and even in the first order, right? So we can see it this way. Although we practically we don't really need to do it this way if we know the integrating factor method already. Okay, so then the way that we solve the non-homogeneous second order ODE that we learned last week, I believe will be the one that you see most often. Okay, but there are a couple, two more methods that I'll introduce, but you probably won't see them very often. Okay, so but I'll just also talk about them anyway. So one is called the variation of parameters. Okay, so again we start with this linear second order ODE, right? So and suppose I know the complementary solution already. Okay, suppose I know the complementary solution already. So the method of variation of parameters is that we try this form as the particular solution. Okay, so what is difference between this method and the previous method? Okay, in the previous method, when we take the trial solution, what we were based on is the form of this g of x, right? So if the g of x is a polynomial, then the trial solution is also polynomial, right? And so on. So here, okay, we don't really look at the form of g of x, but here I just try it in this form. Is that you can see that what I'm doing here is that I have my y1, which is one of the complementary solution, multiply it by some function u1x, which is unknown yet, something we want to find out. And then another solution. Okay, so there another solution y2, which we had here. Okay, multiplied it by the other unknown function u2. Okay, so this is it, right? So we hope that we can find a particular solution that takes this form. Okay, so and u1 and u2 are known. So then, of course, if this one is indeed the solution, right? So if you plug this whole expression back to your ODE, then it has to be satisfied, right? So then let's take the derivative for yp, right? So if you take the derivative for yp, right, using this using product rule, right? So this is what you get here. Okay, so now, okay, so we have the degree of freedom to actually simplify the problem a little bit. Is that we basically say that, okay, so the u1 and u2 we are looking for has to satisfy this relation. So what it means is that this whole term goes to 0. Okay. So if u1 and u2 indeed satisfy this, then of course the problem will be simplified, because now you don't have the first term in this bracket. Then you move on to take the second derivative. Then you don't have too many terms, right? So now if I just put that requirement, and then we go ahead and take the second order derivative, right? So just for this term, right? So using product rule, then I'll find that the yp double prime is given by this. Okay. So now we actually put this one and this one here back to the differential equation. Okay. So then if you do that and then rearrange terms, you'll find that you have this group and this group. Okay. And of course, okay, by definition, okay, these three terms sum together has to be 0 because y1 itself is the complementary solution of the ODE, right? And also y2 itself by definition, right? So I told you already is that is also a complementary solution of the ODE. So that's why this one and this one is 0. So what's left is this, right? So this two terms equal to G, and also one of the requirement that we made in the last slide is this one, right? So it's the star and then the double star here. So now that we have two equations that tells us something about U1 and U2, right? So at the end of the day, all we need to do is find out U1 and U2, right? Because we said that YP is U1 Y1 plus U2 Y2. So if we can find U1 and U2, then we are done. So then here is basically is a two equation, two unknown here. Okay. So let me just, in case you don't see why this one gives you these two. Okay, let me write down the steps. Okay. So this is essentially is a two linear equation, two unknown, right? So and then what are the unknowns? The unknowns are this U1 prime and this U2 prime. So let me rewrite this in this form. Okay. So let me rewrite this here. Okay. So here you can write it as, I'll write it as a matrix form. Okay. Right. So if I write this 2x2 equations system, this linear system as this 2x2 matrix, okay, it will be like this. Okay. So that means, right? So that means the U1 prime and U2 prime is given by the inverse of this matrix, right? So multiplied by this column vector here. Okay, and how do you find the inverse of a 2x2 matrix, right? So if you have a matrix A, which is given by this A B C D, then your A inverse would be 1 divided by the determinant of A, right, times this matrix here. So then that's why, so this inverse, right, so it is 1 divided by the determinant of this matrix. Okay. And the determinant of this matrix is, we had a name for it, which is called the Wronskian. Okay, so that's what we had from last time. Right, so the Wronskian. And then times this matrix. Okay. So then from here, you'll find that the U1 prime is given by this minus Y2G divided by W Wronskian, and then this U2 prime is given by this. Okay. So of course we are not done yet. We have expressed this U1 prime and U2 prime in terms of Y1 and Y2, but we still don't know why U1 prime and U2 prime yet, because we still need to solve these two ODE first. Right? So here, okay, how do we solve the ODE, right? So in principle, so these two, the way that you do it is to use just the integration, right? So because the U1, right? So is a function of x, right? So and then this Y1 and Y2, right? So also function of x, right? So and then so you integrate both sides. For this, you should get U1, and then here also, when you integrate both sides of this equation, you should get a U2. Okay. So then therefore, okay, so therefore, the YP is given by this one, right? This whole thing with this minus sign is U1, right? And then this whole thing with this this whole thing here is this U2. Okay. So then the question is whether you can do this integral or not. Okay, so we'll just have one simple example here. Okay, so in fact, okay, so this one even without the method that I just talked about, you can solve it already, right? So using the trial solution that you learned from last time. Okay, but anyway, let's try to do using variation of parameter. Right? First step, okay. First step always is to find out the complementary solution first. I find out the complementary solution. So this is it. Right. Now I set that, right. So I will try this YP, right. So which is given by U1 times the first complementary solution plus U2 times the second complementary solution. Okay. And then using the two equations, right? So we have, right? So is that this one equals 0? So which is the equation star here, right? And then also the second one is this equation 2 star here, right? So then equation star and then equation 2 star, double star. So and then now you can find that U1 prime. So as a function of Y1 and Y2, which is a function of X only. And then similarly, you find that this U2 prime as a function of X also. So, and the Wronskian is this one. Okay. So then basically what you have here is just a bunch of exponential functions. Okay, so here also. So then this U1 prime is basically just an exponential function. And of course, you know how to integrate it. Okay, but here you just need to be careful is whether this k is equals to 1 or not. Okay, so for k is not 1, then you integrate, give you also an exponential function. Okay, but if k is 1, then this whole thing is just a constant. Then after you integrate, you just get a linear function in x. Okay. So similarly, okay, for this U2 here, right? So just integrate. So then here you get the U1 and U2, then you are done, right? So that's the particular solution you get. Okay, and of course the answer would be exactly the same as if you just use the trial solution, right? So saying that the particular solution is simply given by, right? So if you just use the method you learned from last week, so you just say that try YP equals to a e to the kx. So that would what you would have done, right? But of course, you also need to you look at this and this, right? So you also say that okay, if k is equal to 1, then you actually will try this, right? So k equals 1. or -2. Because again, as I said last week, right, so the particular solution and the complementary solution cannot be linearly dependent. Okay, otherwise that particular solution is not considered to be a particular solution. So another method that again you won't use a lot. So this is again known as it's called the exact equation, but it is actually not quite the same thing as what we had with the first order ODE. When we talk about exact equation, we were thinking of this exact differential and things. Okay, but anyway, for this second order linear ODE, okay, so suppose I have this general form. Okay, so this equation, I'll call this an exact equation if it can be written as a sum of these two terms. Okay, and each term is written as a first order derivative. Okay, so you can see that if this equation, okay, can be indeed written in this form, it will be easier to solve, right? Because you just need to integrate both sides, then you just eliminate this derivative out here. Then essentially you just have a first order differential equation. So then the question is, how do we know whether this equation here can be rewritten as this form? Okay, so then what we do is just to compare the terms. Okay, so we actually do the derivative. So if we actually just do the derivative for these two terms, just using product rule, right? So to expand all the terms out. Okay, and then group it into three terms, right? So the term with y double prime, the term with y prime, and then the term with y. Okay, so then right, so then this equation, right, so is completely equivalent to this equation. So now we compare whether, right, so we compare this form and this form here. So if this is if this one can be indeed written as this form here, right? So then what we require is that this Q of x, right, has to be written as this P of x plus F of x, right? And then R of x has to be written as this F prime x. So that means we need to have this. So if we take the derivative for the first one, okay, so what you get is Q prime x equals P double prime x plus F prime x. And F prime x is actually this R of x. So that means if you have ODE, right? So with this capital P, Q, and R as the coefficient functions, and if these coefficient functions satisfy, okay, so this relations, so then that means this whole equation can be rewritten as this form here. Okay. Right, so this is same as what I said here. Okay. So that means, okay, so if you see this equation, of course, why do we need this method? Okay, if these are all just constant functions, of course, we just use the auxiliary equation, and we know that the solution is e to the something or sine cosine, right? So don't worry about this one at all. So it's just that when we have this PQR as to be some function x, right? So then we don't really know how to solve, then we try whether this one can help us. Okay. So again, some examples. So first example, okay, y double prime plus x y prime plus y equals 0. Right. So this cannot be used using the method that we have learned, right? So then we see, okay, whether this equation is exact, right? So so then what do we test, right? So this, for this case, right? So my capital P is just 1. Okay, so my capital Q is x, and my capital R is 1, right? So then we take these 3 functions, and then we do this test, right, to see if it is satisfied. And indeed, it is satisfied. So that means the ODE can be written as this form. Okay. So then what is f of x? What is f of x? So f of x, from here we can see, okay, f prime x is given by r of x. Right? So f of x is just the integral of r of x. So the integral of r of x is just integrating 1, right? So that's just x. Okay. So then that means this equation itself, okay, can be written as this form. Okay. So and then because these two are both derivatives, then you just direct integration, right? Direct integration, you eliminate one derivatives. Now you have this y prime plus xy equals some constant. So then this is just becomes a first order ODE, and you know how to solve. So the second example here. So a second example here, right? So this time you can see that your P of x is 1 again, and then your Q of x is 3x squared, and then your R of x is x, right? So using this PQR, okay, and then go back to here, right? So use this test here, and then to see whether it's exact, right? So and this time you see that, okay, so this is not exact. Then you cannot use. So what does that mean? So that means you cannot use the method in the previous slide to solve this equation. Okay. Okay, so next we'll move on to a very brief discussion of this even higher order ODE. Okay, but before that, I would just like to go back to one of the tutorials problem that we did not do last Thursday. Okay, so we did not have enough time to do last Thursday. Okay, so I just want you to try this one. Okay. So again, so this one, okay, so and then if you look at this, oh, again, it doesn't looks like something that you are familiar with. Okay, but here I just want to show you that sometimes when we see the ODE that looks unfamiliar, okay, again, we try to use the trick of some change of variables or substitution. Okay, so to convert this equation to a form that we are familiar with. Okay, to a form that we are familiar with, and then in order to solve this, because for this one you can see that if even the right hand side is 0, even if a homogeneous case, it's okay. So you also we cannot also just use the auxiliary equation, right, to solve for the solution, right? Because these are not constant coefficients. Okay. So then if we don't even know how to have the complementary solution, right? So then we couldn't even try the variation of parameter, right? So to find a particular solution. Okay. So, but here, okay, I give you the hint directly, right? So just use this substitution. Okay, try to use this substitution. Okay. So this just to test whether you are good at using chain rule. Okay. So just take a couple minutes to try this one. Okay. Okay, so dy dt. What is the relation between this dy dt and this dy dx first of all? Right, so by chain rule, right, so dy dt would be dy dx dx dt. And this dx dt, what is this dx dt? So dx dt is just d to the t, right? So then this dx dt is just e to the t. And you notice that this e to the t, of course, is just x itself, right? So then this is just x times dy dx. So then first, right, so you see that this x dy dx is nicely replaced by this just dy dt. Right. So now let's also take care of the second order derivative, right? So eventually, so we want this d square y dt square to appear in our equation, right? So this d square y dt square is ddt of dy dt, right? So then this ddt again by chain rule would be this dx dt times dx of this dy dt, right? So just now we know the relation between dy dt and this x dy dx. So first of all, right, so the dx dt, again, it's just x itself. And then I use a product rule for this derivative here. Right, so if I use product rule, what I have is dy dx plus x times d square y dx square. Okay. So that means now you can see that what do we want here? So you see that this x square d square y dx square appears on the right hand side, right? So and that's exactly what appears in the equation. So let me just express this x square d square y dx square in terms of other terms. So that's equals to d square y dt square minus x dy dx, right? And this x dy dx, just now we know that this is dy dt. Okay. So then we have everything we need, right? So this is the first one we need. This is the second one that we need. So then the left hand side, right? So the left hand side of this equation, right, will be converted to right. So the left hand side of the equation is now converted to this. Okay. And the right hand side, what is the right hand side? The right hand side log of x is just t. Right. So that means the whole equation is just this. So linear second order ODE with constant coefficient. Okay, so although it is not homogeneous, but you know very well how to solve it, right? So I'll just write down the answer. So the complementary solution would be, so if you solve this auxiliary equation, you find a double root, right? So then your complementary solution will be this. And then the particular solution. So the particular solution, how do you find the particular solution? Well, you see that the right-hand side is a linear function in t. Then you try this particular solution in this form. And then you just substitute it back to the equation. You'll find that this is equal to t plus 2. Okay. So then this is the solution, right? So yc plus yp. Of course, at the end, so this is y as a function of t, right? So by the end, you want to go back to y as a function of x, right? So just convert all this back to x. Okay, here actually let's take a break. Okay, so let's take a 10 minutes break. We'll come back at 12:30. Okay. Okay, so let's continue. So we have finished everything about the second order ODE. Okay, so then next, I'll give you just a very brief overview of the so-called nth order ODE, right? So n is any number. Okay, so can be 3, it can be 4, and so on. Okay, so we could imagine that in general, of course, it will be very difficult to solve this kind of ODE, right? So you have this higher and higher order derivatives in your equation. Okay, so but still, okay, I'll give you some very special examples that we could actually solve. Okay. But okay, first, okay, so again, let's go with this generic form, okay, of this ODE, right? So this is, what is this? This is an nth order linear ODE, okay, and non-homogeneous, right? So you can see that, right? So the highest derivative that appears in the equation is the dn y dxn, right? So this is the nth order ODE. But still, all the coefficient functions, okay, are just x, but and so that's why this is still a linear ODE. And then the right hand side can be non-zero, so it's not non-homogeneous. So when we solve first order ODE, right? So well, to find the solution, right? So you need to provide an initial condition, right? And then when we solve the second order ODE, right? So you also need to give initial conditions, but that initial conditions not just one number, but it's 2 numbers. Okay. So then you can imagine that if you have third order ODE, right? So your initial conditions is defined by a set of numbers, so 3 numbers, right? And then if it's fourth order ODE, right? So you need to give me your initial conditions should contains 4 numbers. right? So the numbers are this one, right? So at some particular x value, okay, give me the value of y, and then give me the value of this y prime, the value of this y double prime, and so on. So here, okay, so first is a theorem, is that suppose all these coefficient functions are continuous, okay, in some interval, okay, so all these coefficient function and also the gx are continuous, then there will exist a unique solution, okay, provided that you have given all the initial conditions. Okay. So, and now, okay, let's look at the case for this. Again, is the homogeneous ODE. Okay, so the right hand side is 0. So the right hand side is 0. Okay, so then this is the equation. And then remember for the second order ODE, right? So we can find two solutions that are linearly independent, right? And then we said that the linear combination of these two solutions will be the general solution of this ODE. Okay. So now, if I have an nth order ODE, okay, so then you'll be able to find n solutions, okay, which are linearly independent. And then the linear combination, okay, the linear combination of this n solution, okay, will be also a solution to this. And in fact, that is the general solution to this equation here. Okay. So here I talk about the definition of linear independence, okay, for two functions, right? So basically, is that whether one is the scalar multiple of the other, right? So, or you can use Wronskian, but that's the basic thing, right? So is that whether one is the scalar multiple of the other. Okay, so what about the more than two functions? So for 3 functions, 4 functions, how do we say that whether they are linearly independent or not? Okay. So of course I gave the definition here, but before that, I want to give you a picture. So when we talk about this linear independent, okay, so these terms are actually comes from linear algebra, right? So and if you have learned about vectors, okay, you might have also have heard of this linearly independence. Okay, so that's why I want to give you a picture. Okay, so how do we think of this linear independence, okay, for more than 2 functions? Okay, so, and in fact, the picture I'm going to talk about is how do we think of linearly independent vectors. Okay, so for a moment, let's put functions aside. Okay, so let's think of vectors. Okay, let's think of vectors. So if we have this case of 2 vectors, okay, so let's say one is this v1, and the other is this one, okay, v2. So v1 and v2 are parallel to each other. Okay. So if v1 and v2 are parallel to each other, okay, so then v2 can be written as some constant times v1, right? They are parallel to each other. So then basically what I'm saying that, right? So v2 is a scalar multiple, right, of the other. Okay. So now if I have two vectors, right? So, but this time, they are not parallel to each other. Okay. So that means you cannot find a constant k such that v2 is equals to kv1, right? You cannot find any constant k to achieve that because they are not parallel to each other. So, or in other words, okay. So I cannot, if I consider this, if the two vectors, okay, so are linearly independent, then any linear combination of these two vectors, okay, so you multiply this v1 by some factor and then plus v2 multiplied by another factor, okay. No matter what c1 and c2 you choose, right? So it won't be zero, right? Unless both c1 and c2 are zero. So this is the definition of linearly independent. So the picture you could think of is that if linearly independence for two vectors, that means you have two vectors that are not parallel to each other. Okay. So and mathematically, right, so it can be written this statement. So now we want to think about three vectors. Okay, three vectors. And this time, for three vectors, I want to draw a three-dimensional space. Okay. So I'm going to draw three vectors in this three-dimensional space. Okay, v1, v2, and v3. Okay. So suppose in this example, suppose this v1 is just a vector that goes along the x-axis, and then v2 is just another vector goes along the y-axis. Okay. So and then v3, okay, v3 is a vector that looks like this, but v3 is still lying on the xy plane. Okay. So that means all three vectors are lying on the xy plane. Okay. So in this case, you can see that v3 can be expressed as the linear combination of the other two vectors. Right? So if you just imagine this v1 is your x hat and this v2 is your y hat, then any vector on this xy plane can be written as something times x hat plus something times y hat. So then in this set of three vectors, so v1, v2, and v3 are set of vectors, then we see that, right? So one of the vectors can be expressed as a linear combination of the other two. Then we'll say that these three vectors are linearly dependent. Okay. Okay, so yeah, please try to understand this, because although here in this chapter we are still talking about OD, but in the next chapter we'll move on to talk about vectors and matrix. Okay, this will come back. Okay. So now the second case is that I'll give you an example of free linearly independent vector. Okay. So again, let's say my V1 again is go along the x-axis, my V2 go along the y-axis, but this time the V3 goes something like this. Okay. So this V3 is not on the xy plane. Okay, this V3 is somewhat pointing up. It has all three components. Okay, x component, y component, z component. So in this case, right? So you can see that this V3, okay, this V3 cannot be expressed in terms of this V1 and V2. Okay. So V3, right? So you cannot. That means you cannot find any finite value K1 or K2 such that this V3 is can be written in this form. Okay. And of course, okay, of course, you also need to make sure that, okay, so you also need to make sure that for V1, okay, okay, whether it can be expressed as a linear combination of the other two. Okay, so that means in this set of three vectors, okay, so if you cannot find at least one vector that can be expressed as a linear combination of the other two, then we'll say that these three vectors are linearly independent. Okay, and mathematically, the statement is the following. Okay, so C1 V1 plus C2 V2 plus C3 V3 won't be zero unless right. So if you find this, if you find that this is true, right? So then these three vectors are linearly independent. Okay. So it's difficult for me to give you an example with four vectors, but because I cannot draw a four-dimensional space. But you could see that the idea can be generalized, right? So it's just that now not just C1, C2, and C3, but C1, C2, C3, and C4, and so on. Okay. So now, okay, that's easier to think about, right? So the vector, so you can think of these arrows pointing in different directions. Okay. So then when we talk about functions, so basically you could just see that the idea is the same idea is borrowed from here, is that if we say that there are n functions that are linearly independent, okay, over some interval, then we need to consider, right, so the linear combination of the n function. Okay, so you find that all that add together is zero only happen if all these coefficients are zero. Then you say that this set of functions are linearly independent. And now remember Wronskian, okay, Wronskian that we used for this two functions. Okay, remember that in the case of two functions, the Wronskian doesn't seem to be bringing us much convenience, right? So because if you have two functions, you just see whether they are scalar multiple of each other, then you know that linearly independent or not. Okay. However, okay, here if you have more functions, okay, so then Wronskian becomes a very handy tool, right? So to test whether the set of the n functions are linearly independent or not. Okay, so this is the definition of the Wronskian, okay, for n function. Okay, so for two functions you have a 2 by 2 determinant. Okay. For n functions you have n by n determinant. Okay, so the first row you just put in all the n functions, and then the second row you put in the first derivative for all the n functions, and then so on. Okay. So then again we'll see this whether we'll go to calculate this. Okay, if you find that this Wronskian is non-zero, okay, so for some x, just for some x, not always, then you say that these n functions are linearly independent in that interval. Okay, so this slide is right, so it's the same as what we have. What we have over here, right? So for the two functions, for the two functions, yeah. So Wronskians to be 0, so and that means these two functions linearly independent. Okay, and remember that I put this almost always true. It's actually not always true, but at least for the case that we consider, okay, if these functions are actually the solution of the ODE, then it's guaranteed that it's true. Okay. And on the other hand, if these two functions are linearly independent, then that means that the Wronskian is non-zero. Okay. So the statement really is the same. Okay, so but just now we have this n by n determinant for the Wronskian. Okay. So now let's try to just do two very special examples that we can solve. Okay, so third order ODE. So this is a third order ODE. Okay, so now again we in this special case, okay, so we just use the same strategy, is that I assume that the solution, okay, is given by this e to the Rx, right? And then you just plug it back to this left-hand side, right? So then again, what you obtain is an auxiliary equation, right? So, and you find that again, this time, okay, this equation for R is not a quadratic equation, okay, but it's a cubic equation, So whenever you have a cubic equation, then of course you have three roots, right? So here, right, so we indeed have this three roots here. So and now, okay, so then this general solution would be a linear combination of these three solutions here. Okay. So of course, this one is not really a real third order differential equation if you look at it, because if you just let u equals dy dx, right? So you could basically say that this equation is the same as d squared u dx squared minus u equals 0. So this is just equivalent to a second order ODE. Okay, so now I have these three solutions. So let's try to verify whether the three of them are actually linearly independent, right? So we can use the Wronskian. Okay, so the 3 by 3 determinant. Okay. So what is the Wronskian in this case, right? So this is my y1, right? So this is my y2, and this is my y3. Y3 just 1. So my 3 by 3 determinant for Wronskian is y1, y2, y3 for the first row, y1 prime, y2 prime, y3 prime for the second row, y1 double prime, y2 double prime, y3 double prime for the last row. right? So okay, let's not actually spend the time on doing the determinant, but you know how to put in all the values here, right? So e to the x, e to the minus x, and then 1, and then the second one is e to the x minus e to the minus x, and 0, right? So but okay, so again, okay, another example which is simple enough for us to solve. Okay, so again, constant coefficient, homogeneous, right? So this time, okay, you'll find that your auxiliary equation, okay, looks like this. Okay, so I do have 3 roots, okay, but they are just all repeated roots. Right. So remember what do we do with the repeated roots, right? So you need to make sure that all 3 solutions you got are all linearly independent, right? So that's why your first one is e to the x, but then the next one you need to multiply by a extra factor x, and then the last one you will have to multiply by x squared. Again, you can try to use Wronskian to verify that these 3 solutions are indeed linearly independent. Okay. Okay, so now let's move on to part 3 of this chapter, which is a short part, but this will be somehow related to the next chapter. Okay. So here, what we'll talk about is not just one single differential equation. Instead, it's a system of differential equation. Okay. So basically, what I'm considering is the following. Okay. So dx dt is given by, okay, so ax plus by. Okay, and then this dy dt is given by cx plus this dy here. Okay. So this a, b, c, d are all just constant. Right. So this whole system, I still call this a linear. Well, it is still it's a linear system of ODE because all the equations here are still linear. Okay, and but here you can see that the 2 variables. Okay, so the 2 variables are actually connected to each other. Right? So because the rate of change of x, right, not just depends on the x itself, but also depending on the other function y. Okay. So similarly, right, so the rate of change of y depending on also both x and the y function. So then to actually solve this system of ODE, okay, we don't know the method yet, but what you need at the end is a pair of functions, right? So you need to tell me x as a function of t, right, and then also y as a function of t. You give me the 2 functions, and these 2 functions have to satisfy these 2 ODEs simultaneously. Right. So one of the methods to solve this is to use the method, the so-called the method of elimination. Okay. And this method of elimination is, the idea is basically very similar to what we do when we have this 2 by 2 linear equation. Okay. So okay, so this is the the system that we are considering. Okay. So by elimination, that means that I want to eliminate one of the variables. So let's say I want to eliminate y. Okay. So that means I want to express y also in terms of x. Okay, somehow. So how do we do that? So the strategy is that first, okay, so if we take the derivative for the first equation 1, okay, so then I got this, okay, and then I substitute this equation 2 into this equation 3, okay, so that means, right, so I have this dy dt here, but this dy dt is given by this equation 2, then I have this equation here, okay, so now what I have here is an equation that contains the derivative of x and also x itself, okay, but not the derivative of y, okay, but here I still have a y variable here. So, and then what we do next is that again we use equation 1, okay, one more time, okay, because y can also be expressed in terms of this dx dt and x, right? So then if we do that, right, so eventually, right, so you got an equation that only contains x and the derivative of x, okay. So this is a general procedure. It doesn't matter. It doesn't matter what A11, A12, A21, and A22. They are just constants. But as long as they are constants, you can do all this. Right? Of course, if one of them is 0, then the whole thing will even becomes easier. So, but regardless, okay. So now I got an ODE only in x, right? So then I know how to solve this, right? So although the price is that now you need to solve a second order ODE, okay, instead of a first order ODE, but still, okay, so this is something that we know, okay. So then from here, right, so you are able to solve for x as a function of t, right? So then you go back to your equation 2 or equation 1, right? So then you'll be able to find y because you know x already. You know x, that means you know dx dt also. Then you'll be able to know y. Okay. So, and this is actually a homogeneous system. Okay, so if we have this non-homogeneous system, okay, can be written like this here. Okay. But actually, the strategy would be exactly the same. Okay, although you have these two terms behind, right? But these two terms are not something that we can eliminate, right? So really it's given. But the same strategy is that we are going to find out an ODE that only contain x and the derivative of x. Right? So then using the exact same procedure, right, with all these extra functions in t, then you get this single second order ODE in x, but this time this is non-homogeneous. Okay. So you can see that, okay, so the left-hand side of this is exactly the same as the left-hand side of this. It's just that this is homogeneous and this is non-homogeneous. Okay. So then the same procedure for next, right? So solve x first and then find out y, okay, from the equation 1. So here is an example. Okay, I would like you to maybe at least spend a couple minutes to at least to read the question. Okay. Maybe we don't have enough time to give you too much time to work on it, but at least try to see the situation of the question. Okay. So here we have a system, right? So that contains two water tanks. Okay, so the two water tanks contain salt water. Okay, so and you can see that we have this pipe that input some salt water into this tank P. Okay, so and then there's output from the tank P. Okay, so some salt water from this tank P will flow to this tank Q. And then for tank Q, you can see that there are two outputs. Okay, one will just let the salt water go somewhere outside of the system. And then it also has another output that allow some of the salt water to go back to tank P. So now what we want to find is the amount of salt, okay, in this tank P and in this tank Q as a function of time. Okay. So of course, to actually solve the entire problem, you expect that we will also need to know the initial condition and all that, right? But let's just try to find the general solution, right? So initially, so there are already this much amount of water here and this much amount of water here. Okay, so and the salt water keep flowing in. Okay, and you could imagine that initially, okay, so the amount of salt here might not be the same as the amount of salt here, and then as the times goes on, right? So the amount of salt here, the amount of salt here will both change as a function of time. Right? So first, we need to set up the differential equation, right? So for the tank P and the tank Q individually, right? So here we set that let's say that amount X of salt in this tank and then amount Q of salt in the other tank. So if we look at, right, so the dx dt, so dx dt, so what do we have here? Okay. So okay, one thing I want to also mention is that although the water keeps flowing in and flowing out, but the simple things here is that the total amount of water in this tank and the total amount of water in this tank are actually unchanged. So that means the concentration of salt in these two tanks can change over time, but we set up the system such that the amount of water in this and this are not changing. So you can see that here we input 12 liter per unit time in this, and then here it lost 16 liter per unit time, but also there's a 4 liter go back here. So that means for this one, the amount of water going in is 12 plus 4, and the water going out is 16. And for this tank Q, right, so the amount that going in is 16, but then the output is 12 plus 4. Okay, so the amount of water, okay, the volume of the water is the same, okay, but just that the concentration of the salt may change over time. So this dx dt, if we think about this dx dt, we need to think about the terms that make the salt increase, and then also the terms that make the salt decrease. Okay. First of all, we will have this input here. Right, this input here will give us the amount of amount of water per unit time, okay, times the concentration of salt. Okay, so then this is 12 lambda due to this input outside the system. Okay. So and then the other input, okay, so that means make this X increase is the salt water from this tank Q. Okay, and this is actually given by this 4, right? That's the volume per unit time times the concentration. Okay, so what is the concentration of salt at this input, right? So that depends on the amount of salt, right? So in the Y itself, right? So if there's an amount of salt Y in this tank, then the concentration here is Y divided by, right? So the amount of water in tank Q. Okay, the amount of water in tank Q is always kept at this much. So then these are the two inputs. Okay. So that now there's one output here. So that makes the amount of salt decrease. So then this is a minus here, and this is minus. What would that be? So that would be minus 16, right? So this is 16 liters per unit time, right? Times the concentration of the salt in this tank itself. So then this is what happened for this tank X, tank P. So now about this tank Q. So the rate of change of this salt in tank Q is dy dt. So again, look at the input and output. So this time we have one input, right? So the one input is from tank X, right? So then I have this 16 times the concentration of salt, which is X divided by 100. Okay. So here you can see that I have this minus 16 times X divided by 100. This is plus 16 times X divided by 100, because what's lost in this tank P goes to tank Q. So this is the only gain term, right? So for this tank P, tank Q, and then there are two terms that make it lost. That make it loses some salt, right? So this one, 12, right? So that just go outside of the system is 12 times the concentration of tank Q itself. And then here I have minus 4. Okay. Going back to tank P, and this is minus 4 times, again, Y divided by 100. So then these are the two equations that you got. Okay, so and then if you just try to use the use this method, okay. So what you find is you find that the second order ODE for X, right? So will be equals to I'll just write down the answer here. Okay. Okay, so yeah, you can try to verify after class. Okay, so but I have 2 more minutes, but that's just enough for this. So that's actually good. I'll be able to finish this chapter today. So what we have done just now, right? So we use the so-called the method of elimination, right, to solve for this linear system of ODE. So is there another way to do this? Okay, so that's the thing I want to talk about here, and actually in the next chapter. Okay. So if I can have this linear ODE, linear system of ODE, and if I write it in the so-called the matrix form, okay, so then it will look something like this. Okay. I just write this system as the so-called matrix form. So now the question that we want to ask is that if we applied a linear transformation, okay, a linear transformation given here, okay, so that means transforming from this again, it's a variable substitution, but you could see that just going from this x and y, okay, so to this u and v, and this xy and uv, okay, is related by this matrix here. So this is a linear transformation. Okay. Is it possible, okay, so to make such a linear transformation, okay, and after making this transformation, the system of ODE becomes a form that looks like this. So why do we want this? So what is the major difference? Okay, the only difference, okay, between this system and this system is that you can see that in this system, okay, so we have a diagonal matrix, okay, and this system is not a diagonal matrix, so in general. So if we have a diagonal matrix here, right, so you can see that u and v actually not related to each other, right? Because this system, if I go back to this form here, so I don't use matrix anymore, then the system is these two equations. So du dt equals lambda 1u, and this is dv dt equals lambda 2v. So this system is something that we can solve immediately because u and v are not related to each other. So that means if we are able to apply such a transformation, then we can deal with a much easier problem, right? Then you can solve for u as a function of t, and then v as a function of t, and then of course you need to go back to transform it back to x and y, right? But that is also easy, right? Just multiply this inverse matrix. Then the key is how do we do this transformation? Okay, so to make a diagonal matrix so that this system becomes very easy to solve. So to actually do that, right, so what we are trying to achieve here, right? So this is the original system that we try to solve, right? So and then we say that, okay, so this xy, okay, we transform it to this. So that means this xy can be written as this matrix multiplied by this vector here. And then also, right, on the right hand side, this xy becomes this whole term here. So this derivative, but this matrix, this whole matrix is just a constant. So this whole matrix can actually be taken outside of the derivative symbol, right? Outside of the derivative symbol. Then we take it outside, and then we take the inverse. Then we basically make this matrix to the right hand side. So then this system becomes, right, so the derivative of this u and v, right, is given by this product of this free matrix, right, multiplied by this u and v, uv vector. Okay. So this a product of three matrices, of course, is still a matrix, right, still a 2x2 matrix, but we want this to be a diagonal matrix, right? Remember, we want this to be diagonal matrix. So then we in the next chapter, okay, in the next chapter, we will learn how to do the so-called diagonalization of a matrix. So given this matrix A11, A12, A21, A22, you'll be able to find the corresponding ABCD matrix, okay, such that this whole thing is a diagonal matrix. Okay. So of course, okay, so this is one of the purpose of doing diagonalization. Okay, of course, but the purpose is not just about the solving the ODE, right? But we'll talk about that in the next chapter. So next week, right? So after the midterm on Wednesday, next Monday we'll go to the next chapter. Okay, so that's all about the chapter on ODE. Okay, so